Hello everyone, this is Izhen Li from Northeastern University in Boston, USA. In this video, I will introduce our ICASSP paper, which is Pruning, then Reweighting towards data efficient training of diffusion models. Diffusion models belong to a recent class of generative models which have achieved state-of-the-art generation performance. In this work, we consider the following three diffusion models, including pixel-level denoising diffusion probabilistic model, DDPM, the latent-level masked diffusion transformer, MDT, and the latent diffusion model, LDM, which is stable diffusion. However, diffusion models are known for their high training cost. Several works have considered speeding up diffusion training by the progressive patch size, masked patches, momentum, stochastic gradient descent. However, none of them attempt to achieve efficient training through the lens of coreset selection. To the best of our knowledge, this is the first work to investigate how the coreset size of the training data influence the generatibility of diffusion models. In this work, our objective is to balance the generation quality and the computation cost by dataset pruning. Inspired by the principles of data efficient training for generative models such as generative adversarial networks, we first extend the data selection scheme used in GANs to diffusion model training, where data features are encoded by a surrogate model and a scoring criteria is then applied to select the coreset. To improve the overall generative performance after dataset pruning, we employ a class-wise reweighting approach, which derives class weights through the distributionally robust optimization DRO over a pre-trained reference diffusion model. The proxy and the reference model share an identical architecture, whereas the proxy model is trainable on the selected subset and the reference model is a pre-trained one. In this section, I will introduce two dataset pruning methods. The first is moderated DS. It selects samples that have the closest distance to the class median feature Zj, where the class-wise mean of the embeddings is computed by averaging across all representation dimensions. To determine the distance from each representation to its corresponding class median, the scoring criteria is computed as moderated DS, which is the squared Euclidean distance between embeddings and class medians. Subsequently, with a given data ratio, the coreset DS is defined as all data samples within a distance from the median. The second method is the Gaussian model. The Gaussian model computes a scoring for each embedding sample Zi by the empirical median and the covariance, which is defined as Gaussian, where D denotes the dimension of the Zi. After scoring each sample, we preserve all data samples with scores larger than a threshold, which equals to a certain percentile of the scores, ensuring that the top n% of the highest scoring data points are retained to formulate as a coreset DS. Then I will introduce how we leverage class-wise reweighting to improve the overall generation abilities after dataset pruning. As shown in the figure from the right, distinct differences in sampling abilities persist across all classes. Class-wise reweighting aims to enhance the generation levels from a class-specific perspective by considering these differences between diverse domains. Instances with higher access loss are learnable and worth learning, where the reference models obtain a lower loss, yet the proxy model still exhibits a higher loss. distributionally robust optimization (DRO) from the left adjusts class weights to prioritize classes with high access loss through gradient updates on the proxy model weights, thereby amplifying the proxy model's gradient updating on examples from these classes. So, after we compute access loss for each class, we update class weights by normalization and smoothing. Later, we can get the average or the final class weights by averaging these weights over the training steps T. Here, I want to show some experimental results. We vary the surrogate model as the encoder by exception V3, ResNet 18, ResNet 50 based clip, and DDAE, an unconditional DDPM model on 3 datasets with class labels, including Cipher10, ImageNet, and ImageNet, a subset containing 10 easy classes from ImageNet. The pixel-wise DM is DDPM with classifier-free guidance, and LDMs are MDT and Stable Diffusion. Generation quality is evaluated in FID scores on 50K generative samples. Both DDPM and SD are efficiently inferenced by DDIM sampler with 150 steps respectively. MDD is evaluated with 250 DDPM sampling steps. Considering a more reliable and unbiased estimator of image quality on ImageNet, we adopt CMMD by Diffusion Transformer-based clipped embeddings and the maximum mean discrepancy distance with the Gaussian kernel. We first investigate the data-efficient training of DMs on Cipher10 with low resolution 32 x 32. In Table 1, diffusion models trained on the Pruning dataset size ranging from 50K 10% data ratio to 20K 40% of the data ratio show different generative capabilities. We discovered that the GAN-based instance selection is generalized poorly to DMs, where FID scores are even greatly worse than those of uniform random, which selects data for each class randomly in a unified way. The performance decline is from 4.90 up to 13.91 with the decrease in dataset size, proving that it is difficult to describe the compact feature space by such an encoder and data pruning method where the dataset size is small and the resolution is small. Therefore, we execute tentative experiments on surrogate model encodings, including ResNet 18, CLIP, and DDAE as image encoders. The scoring function is changed to moderate DS, choosing these data samples close to the median. As shown in Table 1, ResNet 18 and DDAE yield more effective coresets compared to CLIP, which achieves lower FID than uniform random. Equipped with class-wise reweighting, DDPM trained on a coreset selected by ResNet 18 and moderate DS achieve as a 6.71 FID score under 10% of the data ratio and an FID score of 4.18 with 40% of the training samples. Inspired by InfoBatch, we consider a pruned data training ratio of 0.75 in annual line to improve further the generation abilities, where DDPM is trained on the subset before 87.5% training epoch and then on the full training dataset until the end. We find that analyzing is significantly helpful in enhancing generation qualities, especially when dataset size is smaller, and our approach outperformed InfoBatch, this lossless training acceleration framework in Table 2. Due to the partial full data training, the training speed is affected by analyzing in Table 3 showing the trade-offs between computational efficiency and image synthesis capability. Our dataset pruning is further extended to masked diffusion transformer on ImageNet. Masked diffusion transformer learns the contextual relation among object semantic parts by masking certain tokens in the latent space. Gaussian models selects a more superior and compact subset than moderate DS while future embedding from exception v3. Furthermore, class-wise reweighting is general to all data pruning approaches and different data pruning ratios. Remarkably, as shown in table, MDT equipped with reweighting on merely 20% of data samples achieve a better FID score than model trained on the entire dataset, which is 13.94 versus 17.11. It demonstrates the possibility of both save training costs from scratch and achieving qualified class conditional image generation. We evaluate data pruning on ImageNet, a subset from ImageNet, by fine-tuning Stable Diffusion, a Stable Diffusion ver. 1.4. The prompt for sampling is a photo of a class name. By computing FID on a total of 50K sampling images in 256 times 256 resolution on the classifier-free guidance, SD, fine-tuned on only 40% of the data, significantly surpasses the model on the entire dataset in the last table. An interesting finding is that all models fine-tuned on the subsets show even better generation capability, highlighting the potential data redundancies in large latent diffusion model fine-tuning. Note that class-wise reweighting is not applied in this case because Stable Diffusion fine-tuned on a subset has surpasses the one on the entire dataset, and thus majority of margin loss from DRO is clipped to zero. At last, I will introduce the author information from this paper. This project is led by Izhi Li from Northeastern University, USA, and we have the collaboration with Yihua Zhang and Sijia Liu from Michigan State University. And this paper is mainly advised by Dr. Sherling from Northeastern University, USA. You can check our released code from GitHub by scanning this QR code. And if you have more questions, we are happy to have the discussion with you via the given email address. Thank you for listening.